You are a lot of people. That's the first time that I'm giving this talk, so you are going to be my test audience. Be nice. I will be talking about something that I normally don't do, that it's exploitation. So this is something that I'm doing in my free time. And that's really free time. That means after work, in the evening, and a weekend, so don't be too hard on me. And as I said before, I'm not a vulnerability researcher, so. But what I am, I'm a reverse engineer. I work with malware, and my whole day is about staring at binaries and trying to make sense of it. I also co-organize and board member of Black Hoodie. For people that doesn't know, it's a reverse engineering bootcamp only for women that we run once in a year in a really big weekend, and also in some spin-offs around the world in different conferences. Also in the program committee of Hacklu, that it's happening from tomorrow, no, from Monday on. I'm also the technical lead of the content at Disobey, one of the conferences that it's happening in Finland. And yeah, and I have a life. So I do mountaineering, I like climbing, I like the nature without computers. And I also want to be a karaoke singer at some point. So what I'm going to talk about is not about this stuff that I do every day. I will try to give an overview of what is constraint logic programming. I just did a copy and paste from my last talk on this slide, so it will work. I will talk about solvers, static analysis, memory, of course, and yeah, the heaps. What happened with this research was that it started as a code verification research. So I wanted to build a tool that verifies code, like this. It doesn't matter. And then I realized, oh, shit, that's hard. And then I decided to make it a bit smaller. And I was, OK, I cannot verify everything at once, so I will try something smaller. I will try to verify the memory. And I was again, whoa, that's also hard. And then I was, OK, let's try even smaller. And then I did it for the heaps. And as you notice from the name of the talk, it's also still not that easy. And people also ask, like, you were talking about set and sem, what is that? They're just solvers. Solvers are something that I started using not in the computer science, but before. I use it to work with another kind of science, not computers. And we use it as SMT solvers a lot for doing verification of theorems. And the set problem, it was something that I was interested in even before I was in the computer science. It's just a problem that is asking if a variable of a given formula in Boolean formula can be replaced from values like 1 and zeros, like true or false. And in the end, it's always evaluating to true. The problem with sets, it's a non-NP complete problem. That means that you cannot just solve it with an efficient algorithm that it's known until now. So if you solve it, I'm pretty sure you are getting a lot of money. Then we have the SMT. SMT is nothing else than like a front end, not like a web application that you just click and click, of course, but it's still like a front end for the set problem. And the difference is, if you try to model programs, code, or anything in Boolean formulas, it's pretty hard, because you just like have and or and some cantons. So it's really, really hard. And then someone thought, OK, I can make it better. I can make it easier. And then they create the SMT solvers that you can also have like equations, mathematical equations like plus and minus. So it's not that easy, but it's way easier than it was before. The problem with SMT solvers is that it's not that efficient. And one of the main issues with SMT theory is to make this front end still be so efficient and reliable as the set are, because set is logic and it works in your hardware by design, right? So, and what is this set about? Normally when I go to conferences, outside it looks like that. That's really nice that here is sunny and everything, but then I don't want to stay here inside, but it's pretty bad. But anyway, set solvers are doing something like that. They are looking at pictures or facts that you know about the situation, and you are asking a question. So you are going to ask, can I go outside without getting wet? And the set solver will reason about this situation that it can see. So it will say, okay, the street is wet, it seems it's raining, but I see people with umbrella, and they are not getting wet. So the set or the SMT solver will answer you, yes, you can, if you have an umbrella. And then you don't have the umbrella. So you can also add this constraint to your program, to your SMT solver, and you say, okay, I don't have an umbrella, and now? And then the SMT solver will reason again. You go through all the facts that it has, and assuming that you don't have an umbrella, it's pretty much impossible to go outside without getting wet. So you'd say, yep, nope, not going to happen. And I was talking about constraints. I have another picture to try to explain what constraints are and how they work. I like to think that it's like a big room, and you want to go from one side to another, like here. And now you know that you can always go through these lines and walk through that, and it's okay. But if you imagine that this room is like a maze, every time that I add a wall in my maze, I have one path less that I can go through to reach the other side. So the constraints are like the walls and the maze. And there was this guy that inspired me to work with the stuff that I was working before and put it together with computer science and security, because I'm a lazy person. I don't like doing the same stuff twice. And I guess that's pretty much everybody here, so we automate the things that we can. And this guy told me that I don't even need to think about how to automate this stuff, because we have computers for it. So I can state a problem, I can say, I want this kind of solution for my problem, can you solve it for me? And logical programming does that. If you write a good enough model, and I will come to that again, it will say to you, or you show how you can solve your problem, or if you can, it will give all the constraints that you have to solve the problem the way you want. And if you don't have any chance to solve that problem, it will also say it to you. You cannot solve it like that. So don't waste your time. So now we know how the SMT solver works. And if you want to talk about how are the internals of the engine and how the logic works inside or whatever, we can talk about that later. But I don't have much time, so I will skip that for now. And we can see these blocks as a black box. So you put your formula. As I told before, the formula is your problem. The constraints that you have, like I have so many cores and so much memory and so much storage, and I want to solve this problem, and my solution should look like that. And everything will be inside this box. It will look at the bigger picture, it will reason about that, and then it will say to you, can I do it or not? And as I said before, the best part ever is it doesn't just say, yeah, it's feasible, you can do that, but it also gives you something that the name is instance of axiom quantum. You don't need to know about that, but they are like solutions, possible solutions for your problem, until you are satisfied. And if you are not, and the SMT server gave you all the possible solutions, it will say, okay, so I cannot solve that for you. And if you think about who was like proving things before. Because code verification is nothing more than proving that something works, right? And the people that were behind the SMT solvers and the set solvers in first place, they were the mathematicians. Because you know, you have like these big questions in the world, like P equals NP and stuff like that. And the mathematicians, they needed to prove small theorems that would infer that a bigger one is right or wrong. SMT solvers were used, for example, to solve the color graphing problem for 3 colors and for 4. So you can also model these kind of problems, just scaling it slowly. And then I thought, okay, if I can do that with math, I can probably do that with hardware. And I can also do it with software. And when I started researching, I saw that, yeah, you have some work done, but not enough. And I really believe that the large-scale verification of code, independent of if it's software or hardware or microcode or whatever, it's possible if you know how to model it in a logical way. People that are doing that, they are the long stack people that our keynote was talking about this yesterday. And they are using SMT solvers for proving that the parsers are working the way they are supposed to work. I don't know how much you people know about the long stack. They are a bit different people, but their work is really important because they are assuming from the language, from the definition of the language, that the code is secure. So it's a beautiful work. It's really interesting. And they are using this kind of tools like Prolog, logical programming, constraint programming, and also SMT solvers to verify their parsers. And what do I do with SMT solvers is I implement the SMT solvers inside the symbolic execution engine that I created. And symbolic execution is nothing more than an engine that will execute your code without doing it with normal input. So what do you have as, I have a slide on that. Yeah, there you go. So you just start your program without giving actual inputs. You have like things that could be. So you substitute a variable to another variable. Sounds silly, yeah, but it's not. And then you go through your whole code using this variable and inferring the next one. And these will create domains of possible input for each branching point of your code. And then at some point, you will get this kind of error that you know that this value is never going to happen, so you don't need to analyze this part of the code, for example. I tried to come up with a simple algorithm. For those who know me, I write code in Prolog, what's a bit different than the normal imperative programming. But that's simplified how a symbolic execution engine would work. It's not that hard at all, if you think about it. It's just like creating states, and for each state, you have also a process that it's going to be saved in a really big tree. So you have this graph with like nodes everywhere. And you can think about the problems right now. The problem on implementing these kind of things is that we don't have the computer power for it right now. And if we have the computer power, you don't have the storage for it. And it's always a balance. Another problem that you have is the performance problem, that it's pretty slow. If you think about that, you need to check every single path. If you have testers here, you know that it's almost impossible to have 100% code coverage. So that's what symbolic execution is trying to do. And I said I would talk about memory, right? So to store information, the memory use something that the name is latches. And this is a really simple one, and/or latch. And if you think about it, it's pretty simple and easy to understand. But of course, inside our computers, it's a bit more complicated. You think about that you have one of these, but you also have this something that it's the read-you-write input. And then you put this together with a lot of others, because this one cannot just store 1 byte, 1 bit. So you need 2 of it. And then if you think about it, that you have a matrix of it, and it's like, if I'm wrong, you have like 128 times 64 to have this really, really old SRAMs that you had like when you were a child, and no one is using it more, about 1 megabyte of RAM. So you can think how small this piece is. But if you go deep enough, it's simple and it's logical. The problem with the memory is, if you think about the layout of it, you have stack, you have heap, you have whatever, right? Everything the same hardware. So what's the difference? And the difference is in the implementation. So how you are implementing the heap and how you are implementing the stack. And there are not 50, don't worry, but I'm not going to talk also about the stack and everything, but simple explained, you could think about like, the heap is like where you have the variables that you put like static in front of the C or whatever. So it's everything in the implementation, it's nothing in the hardware. And the thing is, I could not really define myself better than I learned it from a book. But that's how it looks like. You have like a place where you have the data on the stack, and you have this place where is the heap, and they are like separated. So you can kind of guess where they are. And they are all managed memory. So the good thing with heap is like you have this dynamic memory allocation, so you can like choose, oh, I want to put it there, or there, or there, or there. And another funny part is, if you look at the documentation, they will say like, yeah, memory allocation is unspecified. So you cannot say where it is, because there is no API to retrieve or something. So before, I was talking that I use symbolic execution and so on. So the idea was, like before, my first tool was about reversing malware. I presented like last week, the last time, not talking about that anymore. But it was doing this kind of stuff. Deobfuscating binary code and compiler optimizations were used to define which kind of language I was writing the malware and stuff like that. And then I decided to look at why people are using SMT solvers, because I know they are, but not for malware analysis, the thing that I was doing. And then I realized, okay, they are using like for fuzzing, they are using for code verification, but really small ones, and source code mostly. And they are using for binary analysis, but it's not scalable because they are just using for crack miss. So that's not the real world where we are right now. Crack miss are way too simple. And then I started, okay, but I know a guy that's using it for playing with the same thing that I'm doing. And he's also working on automated exploit generation and also for the heap. So it's possible. If someone else is doing, I'm probably not that wrong. What I tried also is like POCs. I really like to write POCs using Prolog because it's a block that no one can use to really exploit it, but it's still proving that the bug is there. So it's a POC that you can publish on GitHub, and you won't see malware 1 week later using it. So I started to look up. And what I saw was like, OK, everything looks the same. Where's my bug? And then I found a lot of bugs. But they also look like the same. And I was like, OK, I cannot analyze all of this. It will take forever. And OK, let's make it even smaller. That was my life in this research. Make everything smaller, because we were kind of willing too much. And then I decided, OK, I will just care about the exploitable bugs, because who cares about the bugs that are not exploitable at all? No one is going to pay me for that, right? And then I was, OK, now I know what I'm looking for. I need to know how to crash it. And as I told before, I'm not a vulnerability researcher. And full disclosure, I never wrote an exploit in my life, so I still don't know how it works. But I know that it's possible to find it using symbolic execution. I used a really stupid search, and I was able to find bugs. And then I talked with this clever guy that I'm going to say his name in the end. And he had a clever search that was finding it even faster. And that was the moment that I started to think, OK, this research is not that bad. So we started looking into things that are out there before defining what we are going to use to write the real exploits and to find the bugs. So we know that people are doing exploratory testing. It's pretty boring, in my opinion. Then they are doing dynamic intent analysis. It works for small pieces of code. And then they are using abstract interpretation. That was where they get me. They were like, OK, that's what I'm going to. And then I found out, not really. I found something that tools that were using it, but they weren't what I was looking for. So I don't know how many of you know symbolic execution engines, but CLE is one well-known tool for that. It's an open source symbolic executor. It runs on top at LLVM. And then you have, and then we have Manticore, that it's also a really good one, that it's working even, I would say, better for binaries than the CLE. But it's still not what I wanted. And I mean, it's my free time, right? I could do whatever. So what I chose was to, again, do my own tool. So I decided to do write a tool that it was doing forward symbolic execution. What that means? That means that it's not going to search all the paths like the stupid symbolic execution one, but it would reason near the branching point if it makes sense to explore that path or not. And with that, it kind of got really, really fast. Things that I was testing before, and it would take kind of days or even weeks. I had 1.5 weeks. Now it was taking only hours. And hours for symbolic execution is really good. So I was happy about that. And I decided to keep it. So exploit generation. I had a plan. So the first thing that I thought about, OK, I need to find a bug. And that's easy, right? I mean, I know so many good people in vulnerability research, and they are finding bugs like this. Bug. Even with their names, I heard. So I was, OK, that's easy, let's do it. And as I am a theoretical person, I decided to find a good theoretical name for it. So I defined a vulnerable path for an input given that you have a function using this vulnerability with this input. That's the vulnerable path. OK? But that's just the math. So the theorem was I need to define what I'm looking for. So yeah, I'm defining everything. I like math. So the theorem was here, giving a program, automatically find vulnerability, and generate exploit for them. That's the theorem that I want to prove, right? I want to write an automated exploit generation program. The first thing that I was looking for the heaps was the direct influence, because I defined it later in the program, but I did add the thing that if the piece of code that I'm analyzing doesn't depend on user input, it's not vulnerable. So I could exclude this part of code that I didn't want to analyze. So, and direct influence means that every piece of code that is actively getting an input from a user outside the code, that would be a piece of code that I really want to analyze. because that has a direct influence on my control flow graph. And then we have the second one. When something like that happens, I heard people are doing it, but no one cares. And the indirect influence is when it depends on the user input, but not directly. Like in this case, you have the user input. It's doing something in my control flow, but not directly because it's not the user input, but just the length. OK, I have my bugs. The second step, the logical step of it would be, I will check if it's exploitable, because if it's not, I don't care. So that was not that easy. I defined it again, what that means. And I thought, like, if you have something that is vulnerable, like we defined before, and we can write an exploit function that with the same input works, that means, OK, that's exploitable. So the exploit, like, that's how I defined the exploit later. But the thing is, that wasn't that easy. If you think about it, it's supposed to be. Because you have the exploit and you have the bug. Why is it not so easy to verify anymore? Yeah, it took me a while, but I got there. And after I did find the vulnerability, asserting that it's exploitable, I was like, OK, let's continue this easy path and implement the given exploit, right? Because now I can prove that the exploit works, so I need the function. That's also a math problem. It's not that easy to reverse these kind of logical formulas. And I wanted something really specific. I wanted to find an exploit that it's generical, and that means I wanted something that it's actively bugging or poking or instruction pointer. I wanted to have really full control of the code, because I don't want to say exploit that it's corrupting anything. Yeah, it crashes, cool. I wanted to have control of the code. And then I thought, yeah, I am always willing too much. Because then I realized, OK, for a really special case, it's working. But then it just worked the most of the times when I tried to test it again, and not every single time. And then I thought, OK, if it's an exploit that it's generated from my tool, that it's working only for a single bug and not for the class of bugs, but just for one. And it's still, just most of the times, not even for that, small bug is working every single time. Is it really automated? I was like having the feeling, OK, I'm failing here. So I decided to add an extra step on my process. That was the evaluate. That's something that we have like in the physics and in the math. But I never saw it in the computer science, the evaluation part in the end of the theory improving. And I decided to do that for this case because it was interesting. So after identifying my vulnerability, asserting that it is exploitable, creating an exploit that kind of worked, I checked how my computer was doing, because it was really loud. And then I realized, OK, I now have another problem. That's the space. My computer was exploding. And normally, you have that in the symbolic execution, of course. But I guess I learned how to deal with that. And I still had the problem. And the problem here was the state space, because I'm messing with the memory now. So I cannot just put in the memory information that I'm getting from the memory. So I was kind of exponentially copying my memory inside my computer. And yeah, I know, pretty clever. So the first problem that I had was find the heap. That was crazy, and I'm pretty glad I have other researchers doing that. The exploit verification, that was, for me at least, the most fun part of it, to create the exploit direct from my actual code and testing it against my vulnerability. And it was kind of a learning for me to see that it's a kind of a gift of people that can write these things. And then I learned that there is something called the state space explosion, because I had no idea what was happening with my memory, and then I started looking for it, and then I found lots of paper about it, and I was like, oh, I'm getting clever now. And the last problem that I had was environment definition. Because as I said before, my exploit was working just most of the times, and I wanted to know why. And the thing is, that's memory, right? So every time when I run my code, it's somewhere else, and you have the old thing sometimes there. And that was the problem with my environment definition in the beginning. I hadn't defined an environment. I was just doing and redoing and redoing it. And then I needed to define that I was looking for an exploit in a clean memory state. And that was really, really important. It sounds silly, but it makes a whole difference when you are talking theoretically. So the limitations. I always talk about this because that's the most important thing that I always think when I am trying to do this kind of work. The Rice theorem, you don't need to understand that, but it's just saying that you cannot assume that one piece of code will always hold when verifying a particular property that you have in another code. And that comes because you can reduce the Rice theorem to the Turing problem. So it's a Turing machine, right? And you cannot put a piece of code inside a piece of code and say that it's going to hold every single time. The second one is the one that I told before, why I needed to define that my exploit, or that my exploit is only, that my code is only exploitable when I am using a user input, because I needed to have my whole theorem inside this bubble of desirable languages. If I have something like without the user input, then I go to the, not just to the indesirable language, but I go to the non-Turing accepted language. And the problem is we don't have a Turing machine for that, so we don't have the computer for that. And we have the practical problems. The practical problem is that I still have a processor inside my computer, right? And a processor is still a finite state machine. That means that it works like a Turing machine. And it's desirable. And if I don't have all my code inside the smallest bubble, it's not going to work, right? So what I learned, that was my first slide from what I learned, that symbolic execution is super cool for vulnerability research too. But then I needed to change that symbolic execution can be a really powerful tool for vulnerability research and exploit generation and all of these things. I will still continue working on it because I like it, and it's my free time. And I have done a lot of other stuff with this, and it works. Yeah, it's scary that it works. But what I decided to work now, it's not on exploit generation itself, but what I noticed is that we need a specialized constraint inference assistant for security researchers. Because we don't know, most of the times, how to define the problems that you want to solve. Remember in the beginning that I told you, we need to have the problem, and we need to know which kind of solution we want to have, and put it inside the SMG solver. The problem is, we don't know the problem, and we don't know which kind of solution we want to have to put it inside of it. And the idea was that if you have a kind of a front end that help people like me that have no idea what I'm looking for, and sometimes you don't have a vulnerability in your code that is exploitable, and you are just a really good developer, I guess. But if you don't know what you are looking for, it's pretty hard to ask. And we are not used to think in a generical way, because it's way more easy to just poke around and you have a shell and you are happy, right? But you don't know sometimes even why it happened. And then you go back and try to understand, what did you do to get that shell? And if you try to go from another side, like I want to have all the shells in the world, and they look like that, and put inside a SMT server to prove that the code is theoretically exploitable, and say to your developer, it's here, it's math, you cannot complain, you need to write a better code. Then you still cannot do it. So what I'm doing now, I'm working on this to help us define what is an exploit and what is a vulnerability that can be exploitable. And the people that I want to thank is Sean Hela, as I told you before. That's the really clever guy that are working on heap exploitation. He have written a bunch of different papers. This is the last one. He is trying to solve the problem that I had really in the beginning, where is the heap? And I also need to thank him a lot for his time, because he is taking lots of his time to discuss with me just ideas and brainstorm, and also inspiration, because sometimes, as I said before in the beginning, I was like, okay, no one is doing that, that's probably stupid. And then I found these two guys. And I was like, okay, it's not completely stupid. Clever people are doing that too. And the second one is Marion, because she was the person in first place that put me in front of assembly code. And if it wasn't for her, I wouldn't be here talking about this. I also used this. It's a bit old paper from Vanegue, but it was one of the papers that helped me how to define all these things in a mathematical way. Because, as I said before, most of the bugs or the exploits, if you try to search for it, you just find, I broke this like that. This code works for this. But you don't have like this generic definition of exploitation or vulnerability and how it's supposed to work in a mathematical way. And he was one of the first trying to define it. And yeah, this was like my friend for the last 3 months, I guess. And I even have it printed pages of it beside my bed. It's pretty bad. So, and that's it. Thank you.